Hi. Welcome to our 2022 May meetup, PyData meetup in Triangle. Please allow me to present our first speaker proudly, Dr. Anne Drillos. Dr. Anne Drillos is a postdoc in the Person Lab at Duke University. Originally trained in computer science and physics, and she's now applying machine learning and statistical technologies to real-time analysis of neural and behavioral data. And she is now currently a Schwartz Foundation Fellow for Theory in Neuroscience and received a 2021 Career Award at the Scientific Interface from the Baruch Wellcome Fund. Welcome, Anne.
Thank you. All right, let me share my screen and hopefully y'all can see that all right. Yeah, okay, great. Thanks for the introduction and getting to give a talk here at our meetup. I will say if anyone wants to interrupt and ask questions at any point, that's super fine. And I'll try to leave a little bit of time towards the end also for questions if you have them. But yeah, so I am at Duke University and I work on computational problems that are applied to systems neuroscience. So basically I'm interested in how to create new machine learning methods that run in real time to help us more intelligently and more automatically dissect how the brain works. And some of what I'll be talking about today can be applied to other fields. I chose to move into the field of neuroscience because I found it a very interesting big data, high throughput kind of problem. And so I've been doing this for the past 4 years. And the work that I'll be talking about today was done under the supervision of John Pearson and Eva Naumann, who are both faculty at Duke University. All right, so a big problem in neuroscience is like a big goal is to understand things about the brain. And that's obviously a fairly large goal, but I think increasingly popular, able to be potentially solved with a lot of our new computational resources. So we want to understand things about how the brain is like wired up, how it's structured, and how it functions, so how it's related to behavior. But so how do we even go about conducting experiments, not just data analysis, that can give us information about the brain? And one of our goals is, to do this in a living animal. We want to do experiments that let us understand brains of living organisms, eventually living humans as well, while they are engaging in a variety of behaviors so that we can do that sort of causal or correlational analysis between neural activity and behavior. And do so at single neuron resolution. So there's this hypothesis that the neuron is this unit of computation in our brains, although there are plenty of other things going on up there. But we're going to focus on this idea of using single neurons and then scaling them up to thousands and thousands and maybe 1 million neurons, and how we can really craft experiments that allow us to understand these systems. So there's been a lot of new technology to physically enable experiments that can help us characterize whole brains. And in particular, like advances in microscopy have let us image really large portions of the brain in animals like mice or fruit flies, and basically the whole brain in things like the larval zebrafish, which is the organism that I am primarily going to be talking about today. And then sort of more excitingly, not only can you optically image basically the entire brain of this animal, you can optically stimulate it. So you can use lasers to also stimulate individual neurons, which effectively gives us a kind of read and write access to this system. But this is great, but as I'm sure you're well aware, you have a wealth of data, but that means that you have a lot of possibilities about what you can look at, and you have this problem of dealing with a very massive data flow. So for images that we're going to take off the larval zebrafish, it can go up to hundreds of gigabytes per hour. And it's, what can we do with all of this data? If we want to actually test some biological hypothesis, during an experiment, you can think about changing one variable at a time, right? Very classic method, and examine the results. But if you're dealing with a system that is scaling up to maybe 100,000 neurons, which is what we have in the zebrafish, testing one thing at a time is going to be a really slow and inefficient way to figure out how the brain is actually doing computation. So instead, we had this idea for tackling that kind of problem of scaling experiments up to entire brains. And it's really similar to this idea of 20 questions, this game of 20 questions. And if you haven't played, it's really great for like long car trips. So it's easy to play this game. Suppose that I'm thinking of an object, and it's your job to ask me yes or no questions to determine what that object is. So, if you've played it, you know that even though I could be thinking of a near infinite set of possibilities, this is a very winnable game for you because you get to pick each next question after hearing the answer to the previous one. So for instance, if I were thinking of a duck, you could solve this by asking a series of questions like, is it smaller than a bread box? Is it a mammal? Does it have webbed feet? And so on. But what if instead I forced you to ask all of your questions at once without hearing any of the answers to them? You could write down a list of queries to easily figure out the duck, but only if you sort of knew what I was thinking about ahead of time, right? You'd need potentially millions of questions to cover every possible object I might be thinking of, much more than 20. And by analogy, you can think about if you had a really large data set and you wanted to look for patterns, you don't just choose something you want to find and then look for it. You might instead do a more sophisticated analysis and gradually narrow your search based on the data that you pull out. Right, so 20 questions, if you play it where you get to pick a new question after hearing the answer each time, it's very winnable, right? And so it's very powerful because we can adapt our next question or our next query or our next piece of analysis to the most up-to-date and new information that we gathered from the last question. Okay, so this general concept of an adaptive experimental design lets us take advantage of data as we collect it. So you don't have to do just post hoc analyses. You can start analyzing and potentially change your questions as you gather data. And so, what we have started to do is apply this concept for neuroscience experiments. And in particular, if you would like to do this kind of adaptive questioning in the brain, you need some sort of real-time data stream and real-time models to give us an explanation of the answer that we are receiving. All right, so what do I mean by talking about real-time models here for neuroscience experiments? And in general, the kinds of experiments that we're talking about are a live organism, like I said, we're imaging its brain, and we're showing it something in particular. In this case, we're going to be showing it a series of moving gratings. So just a projected picture. You could also think about, giving it something to listen to, or different experimental variables. But basically correlating some sort of stimuli, external stimuli, and imaging of the fish while the fish might be doing something like pretending to swim by flicking its tail. So it's a general idea of the experiment. Where does the modeling fit in? And typically, the kinds of experiments that people are running can be quite complex. So there are different tools and different pieces that we would draw from observing behavior or these stimuli that I talked about. The way that we're recording the neural activity can change. There are many different ways to record in the brain. And there's a few different ways to manipulate the neural activity, to stimulate the neural activity, right? So we have all of these kinds of things. And models in particular, of course, are used to give us this quantitative description or inference for whatever system that we're studying. They additionally help us generate new testable hypotheses. So if you're a neuroscience experimenter and you are doing these kinds of these kinds of experiments, in vivo, you are likely constructing some kind of experimental design that is drawing from most, if not all, of these elements. But at least in academia, in the lab, when you are implementing these experiments, especially if you have experiments with real-time constraints, right? These are going to be really lab specific. So built by the graduate students and are highly specific to one particular lab with one particular animal and so on. So they're very difficult to generalize to other labs and other animals, in part because of the tight integration that's required between all of these components. So one of the things that we've worked on over the past couple of years is this software platform written in Python called Improv. It's a flexible platform designed to help us engineer these real-time adaptive experiments. Right, and I'll go into more detail about Improv later, but in general, just think of it as the glue between each of these components in a very flexible way that allows us to adapt to what is currently going on in the brain and potentially change our experiment as we have that real-time data stream. But first, I'm just going to keep grounding you in this example of a particular experiment and how we've used Improv in the lab to allow us to run these real-time models during an experiment. And so zebrafish, like I mentioned previously, are pretty great because you can image basically their whole brain when they're about a week old. This is an image that I acquired in Eva Naumann's lab, and it's artificially colored, but basically you get, just a ton of neurons here. And this is a static picture, but of course, they're all firing at different rates, and you have this very high throughput data problem. And in particular, one thing that Eva's lab studies is this optomotor response. So the zebrafish, which is right there, is going to see moving gratings, these black and white stripes here, and the zebrafish is going to want to swim to align itself with the direction of those moving gratings, right? So optomotor response, basically the zebrafish is going to see things, it's going to do some sort of computation in the brain that we'd like to take a look at, and then it's going to have a motor response by flicking its tail so that it can stay aligned to what it sees as the visual motion. Okay, so this is just another schematic of the exact same thing. We've got the fish under the microscope, it's seeing those gratings, and we're imaging its brain. So this here is a video of the gratings moving under the scope. And this here is a video of what we see in the brain, okay? If we wanted to analyze this data in real time, we would need to do things like motion correction and neuron finding. We're going to do some spatial selection of these neurons and extract their activity, so the intensity in these images, over time. We might also do a deconvolution to look at neural spikes, which is seen as the base unit of activity of neurons. Okay. So if we wanted up to the moment information about the brain, we need to do all of that for all the neurons we see, and we can't look ahead in time, right? So each time we get a new image, we need to immediately process it, immediately update our model before we have time to acquire a new image. So this is what I mean by real time. We do all of our processing and model updating in the time it takes to acquire the next image. Okay, and in general, like I said, this can scale up to about 100 gigabytes per hour for imaging. In practice, the work that I've been doing with Eva is not going to be that high of a data rate, but it still can be quite high. And I'll go into more detail on some of those data rates as well. Okay, so back to Improv, which, as I said, was the nice, flexible, Python-focused package that we wrote to help us do these experiments. And the concept behind this is related to the actor model in computer science, where each step in the experimental pipeline is an actor. So think of an actor on a stage. It's solely responsible for one job. It is not dependent on any other actors. And so we might have a single actor called an acquirer actor, and its only job is to take the image from the microscope and pass it on, right? That's its only job. And we might have a different actor that says, what stimuli am I showing to the fish? And that's its only job, right? And so basically, if we're able to parcel out the experiment into these different actors, what we can do is execute each step. So each little actor has a job, and you can do all of these jobs concurrently rather than sequentially, which really helps with execution if you're trying to pack in all of these things at once before reading the next image. Okay, and so the way this works with improv, we are responsible for instantiating each of the actors, which are going to be user-defined, inside of a separate process. And then instead of having to transfer data between actors, and I told you these images can be quite large sometimes and coming through pretty fast, so you don't want to transfer the data directly. So instead, we're going to put this data into an in-memory shared data store and tell whoever else needs to know a key to say, this is where I put the data, and if you want to go look at it, here's where it is. Okay, so these arrows here in our original diagram of the experimental pipeline are communication, not data flow. So more like execution order there. Okay, and so here I'm leveraging libraries in Python that include the multiprocessing library and async IO libraries, because again, you don't want to have a blocked execution. And importantly, using this, the particular in-memory shared data store, of course, you could pop in different shared data stores if you wanted, but the particular one that we choose to use is called Plasma, which is part of the Apache Arrow project. So basically, this is, like I said, in memory, so it's quite fast to access, and it is a zero copy read operation. So if you just needed to look at the data and use it to update your model, but not modify the data, then you could do this without copying it. And you don't need to copy or deserialize the data. And so this obviously makes for a really, really efficient way to handle the large amounts of data that we have going through. And this is written in C++ with Python wrappers, and I'm not sure if it's been ported to other languages, but it's a great package if you're interested in using it. Okay, so the way this works, this is the same diagram I showed you earlier, where each piece in your experimental pipeline is an actor. And we wanted to make improv super user-friendly so that many neuroscience labs would be able to take improv and adapt it to their particular use case. So all you need to do to spec your experiment, we have a configuration file. It's just a YAML file. And you say, what are the actors? And what package am I supposed to import these from? What class is this? And improv takes care of all of the instantiation and setting up the message passing that needs to go on between these actors and so on. And then the only other bit of information that you need are basically what are the communication connections that you need, right? So for instance, the acquirer, the output of this, and here we're using a custom multi-output async queue in Python. And here, we want it to go to both an image processing actor and a visualization actor so that we can keep the experimenter in the loop. Right, and so you just list out what are the logical flows here. So, and then the class definition, that's all up to the user. But in general, there's a particular flow that we're using here. So for this analysis actor, and this is the one that we're going to focus on real-time modeling. So this is what our analysis is going to be. This is just some pseudocode showing the analysis actor is going to be a mean analysis. We just want to take our new data, which are our neural activity over time, and compute a running average. So like I mentioned, you're going to need to get a key to get the data from the store. And here the get isn't necessarily a copy operation. So you're going to get some sort of estimate of neural activity from the store. You're going to do whatever kind of computation on it that you want. In this case, we're just doing like a mean, for example. And you might, compute a couple of different things and put those results back into the store. We've supplied something called our client here, which is just the store interface, which is easy for people to use. And then once you're done with that, you tell the next person down the line where you put this data, right? So you get the data, you do something to it, and you put different data back in. And basically what this kind of framework allows us to do is this concurrent execution. So if I'm an actor, I'm not blocking anyone else, I'm just waiting for data to exist, and then I can go on and do my operation. So this is super efficient this way.
Hey, Anne, sorry to interrupt, but I see a hand raised up. Mark?
Oh, sorry, I don't. Yeah, I don't see it. Sorry.
Okay. I'll do the job to
Thank
call
you.
people's name. No worries.
Anne, I was wondering if you're doing a running average, where do you set the number of data points prior to the current one that are averaged? I'm pretty sure you don't want to average from the beginning of the experiment. This is a running average. So where do you decide?
Yeah.
Is that from experience or experiments, or how is that interval decided?
Yeah. So in general, the kinds of analyses that we're talking about, which is not usually a running average, are you start from zero. So you start the experiment with improv and you start to collect data. So the first data point you take, that's your average. The second data point, you keep a local, so each actor class has local variables that you can keep around that are not associated with the data store. And so you just keep a count of how much data you have acquired and use this to update your running average. Does that make sense? Sorry,
Mark,
I can't.
Mark, you're on mute.
Yes, thank you.
Okay, sure, yeah. Cool. So yeah, one of the reasons we designed it this way is that you can both be flexible with the design of your experiment, but also run super fast, which is the whole goal here. And if you look at this figure here in our little experiment where we have some sort of pre-processing and model fitting maybe and some visualization, if you ran all of these tasks sequentially, which is typically done, by the time that you got back around to acquiring a new image after all of this, you're delaying your acquisition. It's been too long. You know, in our with our particular implementation, because we're leveraging this concurrency and doing some speed up work as well, all tasks can be completed in less time than it takes to acquire the new image. And so we stay under, in this case, a hypothetical 30 Hertz time budget. And equally important, if you look at basically the gap between acquisition and, for instance, processing the image, right? You need that gap to stay exactly the same. You can't accumulate a time delay. And so here, even if we have a small time delay on a particular frame, we're able to catch up and stay locked to acquisition. So real time here just means that we're staying as fast as acquisition can take place. And then we're also, fault tolerant by design. If, for instance, your acquisition actor stopped working all of a sudden, you don't want to have to shut down your entire experiment. You want to be able to keep going. And because we've separated out each of these things into unique actors, if one of them fails, everything else can keep going while you try to resurrect this one and pop it back in. And so you have this really fault tolerant kind of work so that when you can pick it back up, everything keeps working. Okay, so like I said, this is the kind of design of improv, and we've used it in a lab for these kinds of imaging experiments in zebrafish. So this is just a quick graphical user interface that we've done with PyQt, just a sort of proof of concept, where here we're going to be taking images from the microscope and just displaying them. So this is the raw image. And then immediately we're going to turn around and process that image and start to look at something more sophisticated, which is what we call functional typing of neurons. And basically it's just saying which neuron is sensitive to which kind of stimulus, right? So we're going to be showing the fish some stimuli that are denoted here by color. And we're going to start with a backward moving grading. So the fish sees motion going backward. And immediately in its brain, right here, you can start to see some neurons light up colored purple. And here we've colored it purple because it's responsive to backward motion. We start to show it rightward, forward motion, and you see different neurons pop up and show that they are sensitive to this yellow color-coded motion. And then you keep showing it different stimuli, and gradually, with using sort of circular averaging, you can work out what kinds of visual stimuli these neurons are responsive to. Okay, and then I'll go into more detail about this, but basically here we can also, like I said, concurrently at the same time, do some gradient descent on a particular kind of model and simultaneously fit a model that also tells us basically what sort of connections can we infer in between these neurons as well. Okay, so the first thing that I mentioned, what we're able to do is functional typing. We're able to take a look at the neurons and in real time figure out what they care about. We can use this information to really get a rich picture of how that individual particular brain is encoding what it is seeing. And like I said, we're also doing some model fitting. Here we're using, it's a fairly common model in neuroscience. It's what's referred to as a linear nonlinear Poisson model. And it's just a model that is used to look at the different influences on neural activity. So each neuron has some sort of baseline firing rate, a response to stimulus, you know, a knowledge about whether or not it has been active recently and its connection to other neurons. Okay, you don't necessarily need to care about the exact details here because they're specific to neuroscience, but basically the log likelihood here, we're going to maximize the log likelihood. And because this is a convex kind of problem, we're guaranteed to converge even fitting online, as opposed to fitting a model offline, which is more traditional, using things like stochastic gradient descent. And we can do this in extremely efficiently and find good results of our online fit compared to that of an offline fit, which is when you fit the model with all the data that you have. Okay, so moving slightly away from zebrafish super briefly. Improv in general, like I said, it's designed to work with, you know, any kind of experiment, hopefully. And so here I've replicated an analysis from a different paper here, where in addition to the neural imaging, just like I showed you, we're also going to look at a video, in this case from a mouse, a video of the mouse's face and paws. So the mouse is being imaged in its brain, just like the zebrafish was, but we're also recording what it does as motion output. And we can use an online method of ridge regression to learn what features in this image are predictive of the simultaneously recorded neural activity. Right, and so here X are the behavioral features in the video and Y are the neural data. And what we find is that our regressors that we pick up here quickly basically converge, that we're able to really quickly learn what they are and that they are stable during our experiment. So we get a real-time model of the basically predicting what's relevant in the behavioral video to what's going on in the brain. Okay, so improv is this foundation, and it allows us to handle real-time data streams and use them to refine model parameters online, so in real time, like I just showed you with those two examples. But again, practically speaking, we need to be able to interface with many different kinds of tools. So I've shown you how we work with our specific experimental partner for the fish imaging. And what about other programs or other tools that other experimenters use? Right, not every, so our system is set up to not solve every problem, of course, but it's a lightweight scaffolding approach that allows you to pop things in and out to different actors as needed. And so this allows us to incorporate other tools that would otherwise be hard to incorporate. So batch processing here. not every kind of software tool that people use in neuroscience works in a streaming mode. In fact, that's a lot of our research, trying to transform these models so that you can fit them online. But you don't necessarily need to do that. What we've done with improv is ensure that we're easily able to hook up to other Python packages, for instance, that are doing batch processing. So they need to look at maybe 100 frames of data before they can do some processing and give a result, instead of having a result each frame of data. But we were able to interface with them. We can handle things on different timescales, both a true streaming and a batch processing timescale. We also looked at making sure that we could integrate with different control software. So for instance, in some companies that manufacture microscopes don't like people to mess around with their code, of course. You can't touch the internal of some microscopes, and so you can't necessarily easily send images via Python. But what's really nice is you don't really have to. You can use improv to monitor sort of downstream images instead of needing to get it from the guts of the microscope. We're using also, it's not on the slide, but we're using ZMQ, to also talk between different kinds of control software for things like LabVIEW, MATLAB, and Python. So, the really nice thing about Python ecosystem and this open source code in general is that easy interoperability of many packages. But we are able to interface with more closed systems as well. And then lastly, this actor model kind of framework allows us to easily integrate with other tools, including tools in different languages. And I just wanted to show you a quick example of integration with Julia. So both Python and Julia, if you're not aware already, have packages that are designed to interface with one another. So there's a Python package, PyJulia, which can compile and execute Julia code from within the Python program. And then there's a Julia package, PyCall, to do the reverse. But basically here, what you can see is for a particular actor, we have an example of this in our code base. We might use this Julia module to call this getMean function, which is a Julia piece of code, and use the conversion options so that we're not necessarily copying data between Python and Julia, but we are using a no copy wrapper as long as we're using NumPy. Okay, and then when we actually, so this is just to set up the function, and when we actually run the function in a streaming sense, in a streaming set, we can just simply execute the function as long as it's NumPy array, which most of our images are, and immediately get back the result. So the computation itself is done from Julia, but everything else remains agnostic to this, and the rest of improv runs in Python very easily. Okay, so that's just a little bit about some of the interoperability that we've worked on. Where do real-time models fit in, I guess, more practically? And like, I should say, the online model fitting that we do, you could just acquire all of your data and then fit a model offline. You definitely could do this. But we find it very important to be able to have these online models so that you can adapt the experiment to what is currently going on in the brain. And one of these goals is to be able to stimulate neurons, like I said, we have read-write access, while the animal is active, right? And furthermore, we don't just want to stimulate neurons sort of randomly with no prior knowledge. We want to use those real-time models to tell us where we should be stimulating. And in particular, we want to learn and then stimulate neural trajectories. So neural data across time, neural trajectories. Previously, we looked at a kind of static picture of the brain, and we used online model fitting to lock in a specific picture, right? We're just learning the parameters over time and coming to a conclusion. But now we want to be able to learn, adapt to, and stimulate neural trajectories, again, all in real time. So this is going to be slightly more flexible. The important thing to know here is that we're going to treat this neural activity just as time series data. So neurons are firing and we have that data over time. But in organisms like the larval zebrafish, that's a lot of neurons. And each of those neurons, 100,000. So what we would like to do is, instead of looking at that high dimensional representation, drop it down to a low dimensional representation. So the kinds of neural trajectories that I'm talking about are the latent dynamics, so the lower dimensional trajectories here. So rather than looking at the activity in these 3 neural dimensions, which is just the raw neural activity, we want to instead encapsulate it in a model that is lower dimensional, okay? And so what we did is we built a new method that allows us to do this in real time. First, we made a new streaming method for going from those high dimensional, many individual neurons down to a low dimensional representation of that neural activity. And here, there are existing versions of streaming or incremental things like SVD to get down to that lower dimensional representation. But the vectors that they return can be really variable. You can see it abruptly flipping or changing. And this is quite hard to then build a model on top of if your whole basis set is changing really abruptly across time. So instead, we came up with a new method here that minimizes the change in the singular subspace basis between data points, right? We want something that's consistent through time, fairly stable, but able to track slight changes in the subspace that we're calling ProSVD because it's a orthogonal Procrustes problem solution. So what's important to know here is that after only a few seconds of data seen, so after only a few seconds of images, the derivative of these basis vectors in our low dimensional space has dropped, and we come to a time-stable low dimensional representation of the data. So once we have that data in this low dimensional space, we're going to want to learn a model. And the model that we're using is a Gaussian mixture model. So we have different tiles here with a mean, which is the black dot, and variance, which is the orange. So we're going to want to learn where the data are and put our mixture of Gaussians to cover the data. And we're also going to learn a transition matrix using a hidden Markov model. So what we're going to learn, instead of trying to model like really closely exactly what the data are doing, because the data is kind of noisy, we're going to learn a soft tiling of this space. So we're going to approximate the neural trajectories with this kind of model. And this model is very flexible. You can it can be used to capture basically changes in transitions, so diverging kind of trajectories. And both components of this model, the GMM and the HMM, are fairly easy and fast to compute. So this is just a quick movie showing how this model is fitting the data online, right? So we start from scratch, we start to see data, and then we start to fit this data, and we adjust our fit constantly throughout the experiment. So these are the node locations, and we'd also learn a graph that basically says we're going to transition from this node to this one, to this one, to this one, and so on, right? And so that's the dynamic, the trajectory portion of this. We applied this model to a number of different data types in neuroscience. One of this is electrophysiological data, where here, again, we start from scratch. We start to look at this low dimensional neural trajectories. You can see them being traced out in blue here. And as we see new ones, we can pop in new tiles, that's the orange there, to help us cover the data and learn predictions for where the data are going to be next. Okay, and this model, you can see we're fitting this across time. This is our predicted probability up here. So we're able to quickly learn the model fit, and the entropy that the entropy in our system drops as well. Okay, so we're able to do this fairly quickly with and keep up to date with it as we continue the experiment. We also went ahead and looked at behavioral data, so not just neural data, but also behavioral data, using the same kind of video from the mouse that I showed you earlier. So previously we did this online ridge regression, and now we're going to do this online dimension reduction and look at the trajectories through this space. And so the data itself are not as structured as the spiking data I showed you, but you can still see these trajectories traced out in blue and the tiles that we learned to help generate predictions for motion in this space. And I'm almost out of time, but I wanted to briefly mention running this in that same zebrafish experiment that I told you about, where the kinds of trajectories that we see are associated with the motion of the grating. So when the fish starts to see a grating move across its face, the neural state space runs out here, and when you turn the grating off, it comes back to the sort of rest location. And we're able to, again, continually track what this model is doing. And since we're able to continually track, we can then think about perturbing the neural activity, so stimulating the neural activity as you change this trajectory and start to design new ways to move in this neural state space. Okay, and in the last 5-ish minutes or so, but please interrupt with questions if you have them, I'm going to talk a little bit about performance boosting. So how real time are we actually going to get? The question I actually get from a lot of people is, why are you using Python if you care about real time? Can Python keep up? And I can confidently tell you that in every case we've currently looked at, the answer is yes. So I previously showed you this kind of experiment here, where we're benchmarking the image processing we have to do and getting the neural activity out. And here we're running it faster. We can run at faster than 30 hertz. And the most of the kinds of data acquisition systems here are going to be acquired at 30 hertz or slower. So here we're definitely able to keep up, not a problem. More, I think, excitingly, this bubble wrap algorithm I showed you with the neural trajectories. So we're building a model and we're tracking things across time. We can run that at, depending on the experiment, rates much, much faster than you can acquire the data. So rates at about hundreds of hertz, all the way up to kilohertz. The electrophysiological data is recorded faster than the imaging data, but I think it's still on the order of kilohertz, in which case our modeling should be able to keep up. And then lastly, I want to point out that the predictive aspect of this is what's particularly important. We want to predict into the future, and we can generate these predictions at faster than 10 kilohertz. So again, faster than you can acquire the data, which makes these real-time adaptive designs very possible. And one of the ways that we have been pushing these real-time data processing and real-time model fitting is obviously through accelerated computation. And I'm sure some of you are familiar with them, but just in case, these are the ones that we've used that we really like. So there are a couple packages that we've used to offload some of our computations onto the GPU. So things like CuPy, which is a NumPy, SciPy compatible library that's intended as sort of a drop-in replacement for NumPy. You can also write custom CUDA kernels with it and execute those in Python. And then my current favorite is JAX, which is a research project out of Google, which is bringing together auto differentiation if you need to differentiate through your models for things like gradient descent, as well as accelerated linear algebra. And so you get super fast and automatic, basically automatic model fitting. And you can compile this code and put it on the GPU. And it's quite great. It has some idiosyncrasies if you want to discuss them, but it's a really good way to immediately accelerate your code without having to actually change much of it. You can also, of course, use different languages, like I already talked about, and then pretty easily interface back to Python for anything else that is less time sensitive. And then I thought I'd also mention Python or Python here, which is Python, but as well as C. I haven't personally used it, but I know other people in the lab that have, to help speed up their computation. And then you can accelerate via different math, right? You can choose different ways to fit. You can choose different ways to compute different, things like Cholesky compositions. You should make sure that you know what order, C or Fortran, you're doing your matrix multiplication in, different approximations. And this is less one size fits all. It's going to be very specific to your model. But don't discount looking a little bit at the math if just switching out a package is not going to do it for you. Okay, so I hope I've shown you that a really cool application of Python in the neuroscience sphere is improv here, which combines this real-time model fitting and this notion of adaptive experimental designs to enable streaming analysis and basically new experimental designs that can allow for stimulation of neural activity in real time based on what that current brain is doing in the moment. Our code is open source here on GitHub, and I'd be happy to get in contact with anybody who's interested in running these sort of real-time adaptive model fitting. And of course, there's been a lot of really excellent people who have worked on this, as well as a thank you to the funding sources and to you guys. I'd be happy to take more questions.
Great, thank you, Anne. You're right on time.
Okay.
Wonderful, wonderful. We do have maybe 1 or 2 minutes for questions. Mark, you have a question?
Yes, I was wondering if you were going to attend SciPy conference down in Austin.
So my schedule right now is a little bit terrible because I'm interviewing for faculty positions. So
Okay.
I have not made plans to, but I think I would like to be involved in this community. Yeah.
Or anybody on your team. It doesn't have to be you, but I think that there's probably going to be a lot of interest in that community to hear about improv and bubble wrap and that kind of stuff.
Yeah, I will bring it up at our next team meeting tomorrow. Thanks. Yeah.
Okay. Can I jump in? I have actually a number of questions. I think I can get through them pretty quickly. First of all, his name isn't on this last slide, but I'll be darned if I'm not seeing the hand of Jeff Beck in Bubble Wrap. Did he have anything to do with that?
No, I mean, I know who that is, but he did not.
Oh, okay. Oh, he was just somebody who was always into hidden Markov models and Gaussian mixture models.
Yeah, honestly, it's a very, not common, but a lot of, it works really well in a lot of different kinds of neural time series data. Yeah. Okay,
cool. Next one. There's promise of doing a genuinely adaptive experiment, but if I paid attention well, you didn't actually show us one, right? You didn't actually show us an adaptive experiment where literally the results of the model fitting was used to guide the next, experimental stimulus that was being presented or something like that.
You are very correct.
Okay.
The only adaptive experiments that we're currently doing, which is unpublished work, and I didn't bring it up today, are in that zebrafish experiment. What we're doing is we are fitting a model to learn the relationship between all the different neurons that we see. And we are using this to select the next visual stimulus to display to the fish. So we do have an example use case for this sort of adaptive, actual closed loop kind of design. But yes, you're right. And nothing I showed was actually closed loop yet.
Okay. Then speed is one issue, but the even maybe more critical issue is synchronization and timing. And you need sub-millisecond precision for this and a master clock that's calibrated across devices. And is that a problem you claim to have solved with a Python-based framework that's intended to be as flexible and as interoperable as you want it to be?
Yeah.
The monitor clock says 37 milliseconds in. The spike acquisition clock says 38 milliseconds. I mean, right? That kind of issue.
Yeah. No, it is an issue. It's an issue that we haven't solved on the eFIS kind of recording, so that's a much faster rate. We do have, so within improv, we do have synchronization if you need it for the data. But Primarily, this is going to be on 1 or 2 different machines with just simple timestamping for information flow. And what was the other thing? Oh, the other thing is we, in practice, most of these imaging experiments don't care on the order of 5 milliseconds delay, or jitter uncertainty in the timing.
Oh, but you're talking about spikes? I'm not sure.
I'm
not sure that that's really a fair statement.
Talking about calcium.
For the spikes, definitely we would care. For the calcium imaging, you're looking already at a convolved signal. You're not able to distinguish necessarily 5 milliseconds.
All right, I saw a lot of spikes in this presentation. But
yeah.
Okay, last question. That's fine. But a lot of other experimental software packages will use real-time operating systems and kind of really mandate this for the reasoning of synchronicity. But frankly, I always wondered if it was really necessary. Maybe it's not. Last question.
In our case, it's not so much.
Okay. Last question starts with a joke you've probably heard from software engineering. What's the great thing about standards? There's so many to choose from, and there's so many experimental software control packages out there. And I'm wondering, what's the strategy? Are you guys just better than the, literally maybe 1,000 other ones? Do you have anybody else using it besides the Nominee Lab yet? Or is the idea to have a really good package that's just going to be better? I mean, is there why not you? I mean,
so we have
people who really need this that couldn't use something else that was already out there?
Right. Yeah. Long question. No. So yeah, there's at least one other lab at Duke that is using this kind of thing. I'm not as familiar with the details, but it is our goal to sort of grow this out to a larger user base over the period of the next few years. I'd say there are packages to help run the experiments, but we primarily designed this so that we could test our streaming models, right? We're on the computational end. We want a platform that lets us do all this modeling work, and then without touching anybody else's experimental setup, very gently plug in so that we can have access to the real-time data streams and continue to work there. So we're not actually writing any software to run a microscope automatically. We're just on the data handling end of things and visualization a little bit.
Well, it seems like it's the whole brain of the experimental control. I mean, I saw everything was there. But anyway, thank you.
We interface with LabVIEW that does the control, but we're not actively touching the hardware. Yeah.
So to follow up with that, are you guys doing any kind of image alignment or analysis? Because I'm kind of wondering with the Python and concurrency and global interpreted lock, if you've hit that wall yet in computation in which maybe Python, you might be exceeding its
yeah. Currently, most of the slowest bit of this for these experiments is this image processing. And our collaborators, Andrea and Eftikios, are the ones that have worked previously on an algorithm called Cayman Online, which is a Python package with some C++ backend to do motion correction, image stabilization, finding the neurons, and extracting out their neural activity traces. So I think, there are additional computational techniques there. Yeah.
Anne? Hi. I have a question about the hardware requirements for this, because I was just wondering, other than, brain imaging centers don't typically new software on their computers, but if your brain imaging center was cooperative, could this be even applied in human experiments in fMRI? What are the
there's a sort of, you'd need a different model for the human fMRI and a different image processing probably, but you just pop in, a different image processor in that actor and a different model in this actor, and everything else would run the same. So in terms of hardware requirements, we specifically wanted this to be very accessible to many neuroscience labs, right? So we're running it on a workstation that's a couple $1,000s. It's, you have CPU, you need memory, you need a GPU perhaps if you're going to use that. And in our case, for the sort of initial phase of improv, we put everything that I showed you on a single computer and just hooked it up with a 10 gigabit Ethernet connection to the computer that's actually running the experimental apparatus. So we're quite hands-off, and we can do fairly fast data transfer using, like I said, 0MQ, and then do all the additional computation and suggestion for what to do next in the experiment on our single improv workstation. But you could definitely put it on the same computer as the acquisition system. There's nothing stopping you from doing this. You just need to make sure that you have enough of the computational resources.
Ooh, that makes me want to go back to academia. That's so cool.
All right, thank you. Thank you for the questions, but we do run over around 10 minutes already. So Anne, if you don't mind, could you please, put your email in the chat,
Yeah,
just in case, people can follow up with you on their questions or more interests.
definitely. I'd be happy to, set up a Zoom or team meeting with people if they're still interested in talking later. Yeah.
Thank you. Thank you. All right. Let's proceed because we're short on time. All right. Let's present our next speaker, Dave Faust. Mr. Dave has been with Neo4j as an engineer for since 2014. In his role, Dave works with a wide variety of consumers, from startups to Fortune 50 companies, educating them on the value of the graph database, and graph database data science, so on and so forth. And graphs are, being used right now to power transactional systems, deliver analytical insights, and support data science and machine learning and big data problems. Dave is based in Stafford, Virginia, and he holds a master in information system from George Mason University. Welcome, Dave.
Thank you. Thank you. That was a hard presentation to follow up. So let's see how I do. So thanks for having me. Just get squared away. So as he said, my name's Dave Faust. I am a sales engineer at Neo4j, and I've been with Neo4j since 2014 and have been working with graph databases since probably 2011 or so. So tonight, you're probably going, oh, wow, something about graph databases. Do I really need to learn about yet another database? So tonight, hopefully you'll learn something, try and make this informative. We'll talk about really just an overview of graph databases, where we use them, why we use them, some information about them. We'll dive into some data science. We'll talk about our Python integration, since we should probably talk about Python with this meetup. And we'll do a little demonstration with some of our data science library. So a lot of ground to cover. Feel free to ask questions as you go along, and hopefully at the end of the night, you'll have a better understanding of what graph databases are. And really what we see, as we're getting into this connected data, is the connections in the data are as valuable as the data itself. So understanding, how people are connected, what paths they take, why they buy things, what they might buy next, how people go along routes, how we can find shortest paths, how we can make recommendations, how we can fight fraud, and how we can understand knowledge that we've collected within our organization. So building out these knowledge networks. So the connections in the data are really where we see the value, and where organizations see the value and want to leverage a graph database to really change how they're doing business. And we see that really in several of these use cases, and I'll probably spend more time than you really care about driving in on use cases, but just to understand where we're seeing companies make the investment in graph and what value it's adding. So we see a lot in the drug discovery, understanding how drugs are actually discovered, what that process that they go through. It might be through crime detection, so putting together a knowledge graph, putting together activity of people, building out that community of how people work together. Personalization, everybody wants that personalized experience on the website. So I know, our sponsor here is in the advertising. So we see a lot of trying to understand who that person is that just hit our website. So how can we build out that community when I see a new device that's logged into my website or joined the website? What do I know about that IP address to quickly identify what community they belong to, so then I can start to serve up personalized product recommendations. So we have customers that are really doing that identity management and doing that at web scale. Especially now that Apple's taken away the tracking, we see that more and more important. Definitely fraud prevention. A lot of work's being done in fraud prevention. Our traditional network analysis, which has been going on since the 1990s, but building out fraud networks. How do we understand what a fraudulent community looks like? How can I connect, my contact information, my email address, my phone number, my address, to other people, and we build out a community. So when we do have a fraudulent actor, who else might be involved? So we see a lot of activity done there. Knowing your customer, what is my 360 view of the customer? Compliance, and then feeding this into AI and machine learning so we can understand what people are buying, what's effective. And I know less and less about AI and machine learning, but we'll talk a little bit about that maybe later tonight, but definitely in some upcoming presentations. And again, the graph databases are used when the connections are as valuable as the data itself. So if your data doesn't have connections and you don't really care about the connections, graph databases are not for you. There's plenty of other technology for that. But if you want to understand and make sense of the connections, the connectedness in your data, and that's bringing value to you, then you really want to think about, a graph database. So people ask, what is a graph? So some of you probably know this, so this might be new. If you haven't, we'll just talk about this. Graphs have been around forever, and we saw this in computer science classes. But it's really about the relationships, and it started back with Leonard Euler in the 1700s with this 7 bridges of Königsberg, trying to find the path that went across without duplicating paths. So that was really the foundation, and you can look this up on Wikipedia or other sites to explain it better than I can, but that's really the foundation of it. So as Neo4j, as a company, we invented the label property graph model that's used today and with us and with some of our competitors in the graph market space. So this is pretty much a common model that's being used in the industry today. So I'll just explain this, and I'll make it analogous to a relational database model so we can have some context. But really in the circles that we use are for nodes. So nodes are our things, they're our entities, they're objects that we want to describe. So in this case, we have 3 nodes. 2 of them happen to be people, and 1 is a car. So we think about these objects that we want to model out in our data model. Nodes would be analogous to our rows in the database. And we use labels, so we group labels to classify our nodes in the graph. So in this case, we have a person label on this guy on the left. We have a person label on Anne over here on the right, and we've classified this red node as a car. And those are analogous to your tables. So we want to group nodes. We want to be able to identify person nodes or maybe a car node. And then relationships, which are the bread and butter, the important part about the graph, really tell how these nodes are related. So, how is Dan related to Anne? Dan is married to Anne. Dan lives with Ann. That's a good thing. Ann owns a car. Dan drives the car that Ann owns. So the relationships tell us how the nodes are related. They have a type. So that's drives, owns, married to, lives with. They have a direction. So it's always from a node to a node, from a node to a node. And they just give us that context. How does this make sense? What does this graph make sense? And then we have properties. So those are key value pairs. They're attributes that we can apply to the node or to the relationship. And just as you would in a relational database, have columns in your table that say, I have a name, I have a born, I have a Twitter property. For my car, I have a brand model, a location, lat long. I have an attribute on the drive since. They just give us more context about the graph. And the nice thing about this is I could show this to my wife, who's not technical, and she would quickly understand it. So as we, in my role, as I talk to business analysts or to people that make decisions, this is pretty easy to understand. To understand the context of our data, to understand why these are related, why it's important, and what we're trying to portray or give context to the end user. So this is a labeled property graph model. It's different than RDF. I'm not going to go down that rabbit hole today, but Neo4j and other graph databases use the property graph model. This is just a different view of it. It is our key structure underpinning the graph. And again, we have an employee here as a node which has some properties. They're name value pairs that we store. We can search on those. We can look those up. We can add those dynamically. We have the relationships that tell us the context. Those are the verbs. The company is located in a city. Company as a CEO of Amy Peters. She started on January 20th, 2008. So again, just context about a property graph showing us how we can build these out. And if you any questions, please speak up, please ask questions. So why would we use, a graph database? What are the things that make sense? When would we use it? When we want to store data relationships natively. So Neo4j and some of the other competitors will store these natively. So we're not doing join tables. We're not building relationship joins. We're actually connecting the data as we write it. So once we find the nodes, we can traverse quickly down a long number of hops or connections to find the data that we need. The data natively is a graph. We think about it as a graph. It's not just, a big document that we want to store. It's not just purely transactions or really not densely connected data. We want to use that relationship information to transform our business. We want to know, again, who's in this community. Is this person fraudulent, a fraudulent actor? What's the shortest path to get my delivery from Chicago to Houston in the next 3 days? All these type of things transform the business. And then it allows us to dynamically change the model, adjust the model, add new relationships, add new node types on the fly, a lot more flexible. So again, we can argue about this. And the relational databases do their job well for what they're designed for. What we've generally seen, in my experience, is as we decide to go down more and more traversals or build out deeper traversals where we don't know how far down they'll go or how far the traversal is, the relational database performance degrades just because the number of joins we have to do, self joins. It's a lot more complex to write. If you're doing 1 or 2 joins, those are still really good. And I wouldn't argue against using a relational database, but 6, 7, 30, 40 hops, Neo4j, other competitors in our space can handle that quickly. And the ability for us to change that design, add new data, add new relationships on the fly is really important as you're working through the graph. So you're not dropping tables, copying tables, et cetera, et cetera. You know, relational databases have their place, graph databases have their place, right tool for the right job. This is a little dated, so I'm sure some of the other competitors have probably added in different join logic, but some of them, you know, do these joins in the application. Not everyone has ACID support for transactions, so that might be something of importance. You know, even if you're in like Elastic, you're trying to join keys on the fly. It's just not the optimal solution. These databases have their place, they have their role. Again, if you're looking at relationships and making sense of that, you know, look at a graph database for that. All right. Again, just a summary here. I'm just going to skip through that, but you know, the language that we use, very simple to write, very easy to use. Won't dig in too much of that. And again, as we do this, whiteboard friendly, pretty easy to model. I wouldn't say it's bulletproof. We definitely do need to think about your data modeling, the types of queries that you want to use. But a lot of times when we go on site, it's really easy to take this conceptual model, draw these circles, draw these connections on the whiteboard or in PowerPoint or some other tool, and build your logical model that you can then load data in and start to write queries. So, let's see. So again, like in this case, Acme is a company, Kayla is the CEO. You know, there's some organizations. It's a little bit dated, the device. So we can see, run these relationships. We can take this whiteboard model, modify it, iterate over it, change it on the fly, and then apply it to our business. So you may ask, you know, what are these graph shape problems? When should I think about using a graph database? When does it make sense for that? You know, in this case, we have, you know, customer buying t-shirt, another customer buying a t-shirt. We might want to understand, you know, how similar are those customers? Can we identify some similarities? You know, people that bought product X might buy product Y, so let's make a recommendation about that. On a website, you know, what are the common paths that they're taking? So what might be the next best action? You know, what are common paths that people take? Fraud detection is understanding the relationships. Can we build communities based off of shared identifiers to understand how big that fraudulent community is or the potential for fraud? Identity resolution. You know, if I have different names that are living at the same address, using the same phone number, but they might be misspelled, I can leverage the graph to help with that identity resolution. So, you know, if there's relationships that make sense, we should probably think about a graph. Or they're kind of self-referencing. So hierarchies, we might see this in a multi-level marketing, you know, where you build out a hierarchy. You might see it in your organizational chart, who manages whom, friend of friends. So again, some organizational hierarchy. We see this also in network topology, where you see, you know, network topology as a graph because of the connectedness. That's a good use case as well. As well as data lineage. How does data move through an organization? A lot of companies will use a graph to identify how data moves through an organization. Yeah, varying or unknown depth. We see this in, you know, network management, so moving things through, even like a manufacturing. How does things move through a plant? You know, where are we seeing delays in processing? All of these types of chains. Excellent use cases. And then routes. So, what's the shortest path? How do we do infrastructure? What's the optimal path to get a product from point A to point Z within a certain time period? So lots of different routes and lots of different paths. So just to show you, the other one that's really common is knowledge graphs. So I just want to show you today or this week going on, there's, the Knowledge Graph conference in New York. So just to show you different use cases and what people are thinking about. So here's some of our, Stardog is a knowledge graph company. They're doing work. Another competitor onto text, but UBS Financial Services building a knowledge graph on connecting banks data. LexisNexis, another company doing graphs. Neo4j and graphs there. Accenture on clinical trials and reasoning, very interesting. Let's see what else. Oracle doing graph queries. A customer 360 knowledge graph, Intuit for financial tech. Let's see if there's anything else. Google with some neural networks. Tomorrow, let's just look. IBM Research, how do we do knowledge graph construction from text? So how can I do that? David Meza, Neo4j, NASA build a knowledge graph that's helped them get to Mars faster just by understanding lessons learned. And the reason I want to show you this is, graphs are becoming more and more mainstream. It's not a niche thing that, was kind of a curiosity 10 years ago. It's more and more mainstream. Microsoft machine learning models, Snapchat, real-time inference. Here's Capgemini, Morgan Stanley, BBC graph projects. So you see graphs are more and more. Here's drug discovery for knowledge graphs. And just see if there's anything else on Harvard Medical School. This will be Friday. Bloomberg. You just see the depth of different companies. Fidelity for data analytics business decisions. And you see a lot of the different companies out there. So I just want to point out that, graphs are no longer this niche product. They're definitely mainstream, something you should be aware of. Maybe it's not your day-to-day job, but something to be aware of. But again, just a wide variety, everything from chatbots to data lineage to fraud, risk assessment, logistics, promotions, pricing. The list goes on and on and on. And again, I think the common thing here is these are about relationships between individuals. So we saw that in the Panama and Paradise Papers that are being used now to understand the Russian oligarchy and who they're connected to, where their money lives, ownership, money laundering, fraud. Definitely cybersecurity is a lot of interest. Lessons learned, a lot of interest in drug discovery, research in the sciences, supply chain, network, and IT. So tons of different use cases, tons of different usage. So graph database, a traditional database, probably not all that exciting because it's still, how do you sell a database? You sell it to solve business problems. So probably about 3 years ago, Neo4j started focusing on graph data science. So there was some work done in, the Hadoop world with different GraphX and other libraries. We know that companies want to make sense of the data. They want to do graph data science. How do you figure out which open source tool is there, which products are available? So Neo4j made a corporate decision to invest engineering resources into what we call the graph data science library. And what we've done is we have 50 plus graph algorithms in Neo4j that can leverage, the relationships in Neo4j and in the graph database to make sense of your data. So in our community detection and our fraud, we may have a database that has, a person that has a credit card, a phone number, an address, and an email address, and we may share those. So we may decide that we want to do a Louvain or, weekly connected components against that graph, and then write out a component ID so we can understand how are things connected. So I can do that with the graph. I can do it with these algorithms that are provided by Neo4j, tested by Neo4j, run at scale by Neo4j, and make sure that this works. And we have people that are doing routing that have paths defined in Neo4j between waypoints. So we can do, a shortest pair, a Dijkstra pair, or a weighted path to find the optimal path from point A to point Z, and with sub-second response time. Maybe it's a page rank or an article rank. We're doing link prediction, seeing a lot more interest in embeddings with FastRP or GraphSage. So a lot of work being done in these graph algorithms, work that we continually do to help our customers and to help the community make sense of that. And we'll do a little bit of a demonstration here shortly on this. So how this works in Neo4j is we take our native graph store, we move this into an in-memory mathematical representation. We run these algorithms on that in-memory representation, so it's fast. We can write back to the graph. We can mutate those in memory and use those results, maybe the page rank score, the centrality score, to feed that into another algorithm and build these data science pipelines in memory, and then write results back out or feed those into your machine learning pipeline. So we will have, I think Mark's working on setting up a more detailed discussion by our chief data science, Alicia Frame, on this later this year. Oh, look at that, a double slide. And really, why is this important? Just because those relationships just give us so much more information. They just add value into your machine learning models, into our data science. So we make sense out of those relationships and feed the data into that.
Dave?
Yes.
This is Mark. Since we're a data science community, I think most people who've been around for a while would be familiar with the term word-to-vec. And one of the things that I've seen from the graph algorithms is a node-to-vec. Is that correct in the 50 graph algorithms? Is producing a node-to-vec structure?
Yeah, it should be in the embeddings, but
Okay.
Yeah, there's a node-to-vec. So we've documented all of these algorithms, and I'll talk about how you can get started with this. There's other vendors in the graph data space that have similar algorithms you can use for better or for worse. But yeah, there is a node-to-vec. We do a pretty good job on this algorithm in our documentation. We talk about how it's actually used, give some code samples and some results, and the different embeddings. So generally, we'll use a lot of these node embeddings then to feed into machine learning. So we'll calculate a lot of these and then feed those into some machine learning pipeline. Did that help, Mark?
Mark, you're on mute again.
Yes, thank you.
All right, cool. So I got just a couple more slides here, and then we'll do some demonstration. So again, just to show you, so there's this company out here, or this website that does DB engines, and it just really ranks, based on, I don't know, LinkedIn jobs, social media posts, blog posts, other really things, just the most popular databases. So Oracle's at the top, MySQL, Microsoft, kind of your traditional ones. we kind of pride ourselves that we're at 19th in the most popular database category, Neo4j. In the graph space, just to be transparent, we do have 20. I picked the top 20 here. Neo4j. Cosmos is kind of this, I don't know, hybrid thing. These multimodal show up. ArangoDB is pretty good. Amazon Neptune, obviously they're a competitor to us, so you can get started with Amazon Neptune. You can use that. They have a hybrid RDF, SQL underlying. Janus Graph, that one is pretty much dead. Tiger Graph is probably one of our most popular competitors. They're doing a lot of marketing. They have a graph data science. They're definitely focused on the analytics side. And then the rest of these really end up being more, I don't know, I would say more niche companies. We don't really see those being used a lot by your Fortune 500 or other corporations. So in the graph data space, it will usually be Neo4j, some Arango, Neptune, some Microsoft, Tiger Graph, maybe a little bit of dgraph. And then people will just fall back to, I can do this in Postgres, or I'll just brute force it. I don't need a graph database. So, those are the competitors. And the score just kind of shows you Neo4j being around, being the leader, kind of the gap that we have. But, we definitely don't rest on our laurels and continue to improve. And so for the Python, we know that we have a lot of people that use Python, so we do have this language driver. So we write our own drivers that will talk to the graph engine through our native Cypher language over a binary protocol or through HTTP. So we do use the Python. There are other out-of-the-box drivers. Since this is Python, we'll focus on that. And then there are some documentation for that. So before we jump to the demo, if you want to get started on the database, so there's several ways to actually use Neo4j. I'm sure there are other ways for our competitors. So feel free to take a look at those. We do have a cloud instance called AuraDB. So it's our database as a service that runs in the cloud. You can get started with that for free. It's a small amount of nodes and small amount of edges. I think it's maybe 50,000. But if you don't want to install anything on your laptop or on your network, you can run AuraDB in the cloud. And then you can, if you decide you want to pay more or you want to run it on enterprise, we have other offerings. That might be the last slide. Let's go to the next one. So there's a couple other options. So let's see if I can. Where is desktop? So Neo4j Desktop will actually download a full copy of Neo4j Enterprise Edition plus a couple of our utilities. You can include the Graph Data Science Library. It gets downloaded to your desktop as a single user, fully licensed piece of software. So if you can download to your laptop, you can do that. We have some predefined. Let me see what the next. We have Neo4j Sandbox. So if you just want to experiment with Neo4j, understand what's going on, this is like a 3-day online. You just enter in your email and get added to our email distribution list. But you can launch a free sandbox. We have different scenarios in there. So maybe you want to look at just our movies database or network and IT, Paradise Papers. So you can get started with Neo4j that way as well. I think that's all the ways that we want to get started. So let me just close a few things out here. So we're going to use just this little database here. So I'm going to, this is our Neo4j browser. We see that we're going to build this through Python, but we just have some dummy, web page links. So we have nodes that are connected via links to each other. So our labels are on the side, our links are on the side. And I'm going to try and run this through a Python notebook just to show you how this works. So let's get rid of that. So we also have the Graph Data Science as a service. So, you can download this onto your laptop and include the Graph Data Science library. But if you want to run it in the cloud, it does cost some money. So just to be transparent, somewhere in here I had the pricing. Yeah, not there. I don't know, it's a few dollars a day, so I don't know. It's not free. So it's one way of getting started. So I'll walk through this notebook just to show you. So because we find that in the past we've made Python developers become database gurus and understanding how to load data in. We've written our own Graph Data Science Python library. So we're going to just import this. It's going to make things easier. So let me see if I can. So, it's got a lot of algorithms. We have this library, and it just helps us interact with the database and run these different algorithms. So that's really what we're going to use. It helps us with data frames and other things that Python data scientists know about a million things about. So I'm just going to actually create a connection into my database. What? I don't know how to do that. All right. And we've got, we're running Graph Data Science version 2.0.3. So we've connected to this database here that's running up on Google Cloud. And now we're actually going to run some Cypher. So we're going to create that graph that I destroyed. So we're going to create some pages. We're going to create some links with some weights between them. And if we go back to our graph, we're back to what we had before. So we have these pages, we have these links. So now what we're going to do is we're going to actually project this, graph.
Sorry, Dave, to interrupt you. So can you show us how you create the graph again? Okay.
Yeah, so we're using our Cypher language. So these are just a bunch of statements that say we're going to create a node. Just copy it. And how we do it is we just say create. We're going to create a node. We'll give it a variable. We'll add a label. And then we're going to set p.name. We'll add some properties. Dave. And then once this refreshes, I don't know, this browser acts weird sometimes. So that's how we would do it. I mean, this is really simple because it's only 8 nodes, but now we should have a person node here. So let me just refresh this. Oh, you're killing me. Grab the password. There's probably 20 different ways to get data into Neo4j. As soon as this comes back, we'll be there. Yeah, so we have my person node that I've created. And we have the age and the name. So as we do this in this notebook, we're creating a page. We're going to give it a variable home, about. They all have names. And then here we say home, this node here, has a links relationship to the about page. And the property weight is a value of 0.2. So we're persisting this data in the graph inside of the database, inside of the Neo4j database. So this is persisted data at the moment that's in the graph. And then what we're going to do is we're going to say, I want to create an in-memory graph called example-graph. I want to use the page, find all the page nodes, find all the links nodes, and we're going to use this relationship properties. So we're going to take that database graph and bring it into memory so we can operate on it with some of our graph data science libraries. So if we run this, we have a node projection. We have a graph name called example graph. There's 8 nodes and 14 relationships. And this is how we normally will run the graph data science to bring this into memory, and then we can do different algorithms. Maybe we would do the centrality score, the page rank, or the other data science libraries on this. So we'll just list it out. It's pretty small. It's only using a couple megabytes of memory. So we do a lot of data compression. We make this small in memory. We're going to run it. And then we're actually going to run our graph data science page rank, get some statistics on it. We'll do 20 iterations with a damping factor of 0.85. So again, I don't have to find a Python library or another library to figure out page rank or write my own page rank algorithm. So we will run this. So I just ran it to get some statistics on it. It'll tell me the centrality distribution, how long it took. It took 67 milliseconds to compute our configuration. So we're going to stream that out, get some results back. So node ID 0 has a page rank score of 3.2, 1.05 for 1, 2. So we've run a page rank across this tiny, tiny graph and got some results back. So then in our next step, we want to actually write this back to the database. So we want to persist this in our database. And we're going to call this page rank score. So we're going to take the results of that, attach it back to each one of these pages. So we'll just click on it. We have site B, we have home. They have no property called page rank score. So let's run this. And we get, home has 3.25. So if we come back and we rerun this, now we have a page rank score written back, persisted into the graph. So we can do other analysis or other data science on this type of information. So we may take this page rank score and now extract this information and feed that into our machine learning pipeline or some downstream process that can make use of that page rank score. If it was like node-to-vec where we add vectors in that, we could pass those on down as well. So, trying to make this easy for a data scientist to interact with the graph database, to run these graph algorithms without understanding, all the ins and outs or how do we do this with the database. So it's kind of a focus for us to make it easier for Python graph data scientists to do this. We're going to drop the in-memory graph. So we removed it from memory. So there is no more in-memory graph that we can run graph data science on. So we free up that memory, and our little GDS experiment is finished, and we can go grab a cup of coffee or go grab something to eat because our data science piece is done.
Hey, Dave, can I ask you a quick question?
Yeah, absolutely.
As a data scientist, we always deal with tabular data, right? Those columns and rows. If I really have the opportunity, I would love to transform those tabular data into graph data formats, right? So
Right.
do we have to like you showed us in the Jupyter notebook, create a link or person. So we have to do this kind of thing for every single tabular data table.
Yeah, so that's a good question on data loading. So let's just create I'm just going to create a little simple model here. So let's just do person, and I don't know, let's say so let's say I have a table of person, I have an email table, and then I have a join table. So we have some, we could write Python that would basically, read from that table, construct that statement, and process those in large batches. We have what we call load CSV. So if you have that data in a delimited format, we can read that in and create that from a local system. So, in the previous presentation, they talked about PyArrow. So we're actually baking that into the Graph Data Science library because, we want to make that easier to bring data in and out. I mean, PyArrow is phenomenal at moving data in and out of databases. We have Spark connectors. There's 100, I don't know, as many ways you can bring data in, we could probably do it. So, so there are programmatic ways that we would do this. You're not going to take a million rows and write, create X, create Y. You're going to say connect to the database, load all the person nodes, load all the email nodes, and then let's join those on, find the person, find the email, and create that relationship.
Yeah, this is really good news because for local load CSV, for example, so are you saying Cypher languages, you are using Cypher as native language, right?
Yes.
So are you saying the Neo4j platform, when you call load CSV, it'll automatically identify which is the node, which is the property, and which is the link? We don't have to worry about that.
Yeah, let me actually just copy this. Let me bring this into. It's not magic.
While Dave is doing that, let me make a comment. It's my intention that 2022 and 2023 are going to be a little graph database centric, heavy. And one of the sessions that I thought would be very useful is all the different ways that you can get data into a graph database. So we've seen Cypher that will get it in. Dave has just shown load CSV. There's an import statement. The APOC libraries have something. So there's a variety of powerful, fast import mechanisms if you need them. And I want that to be one of the presentations. Just concentrating on getting data in, and another one concentrating on getting data out. But that's my goal. And if you think differently, let me know.
Yeah, so thanks, Mark. Appreciate that. So this is just really simple. So this is from somebody else. So, we have a file that's policy to customer. So in that CSV file, there's a column that's called customer ID. There's, just make this policy. There's another row called policy ID. So the merge, this is just Neo4j specific syntax.
Hey, Dave, I think we're still seeing Chrome if you're typing somewhere else.
Oh, I'm sorry. Let me figure it out. All right.
You might have to restart the share to get a different window in.
Oh, yeah, thanks. All right. That's cool.
There you go. That looks good.
Yeah, so in this case, we just have a simple CSV, and that CSV may look like so one, two, three. So we're going to say, what this statement does is it'll read this CSV file, and it says, create a node with the label customer. The merge will do an upsert. Find me a node with the label customer with a property customer ID of 1. If that does not exist, create it. Otherwise, let's use that node so we don't have duplicates. Same for the policy. I have a policy ID of 1. And then the line 4 says, create a relationship called has policy from the customer node to the policy node. So this works for probably about, up to 1 million rows. So if you have, 1 million rows, load CSV is pretty easy. As long as we can get to it, either locally through the file, it could be through a HTTP, a website, a URL that you can access. So that's kind of like the lowest common denominator. We built a new tool to help you with that. Probably something to demo. But then, you can write custom Python to do processing. There's tools that are available. Spark connector, yada, yada, yada. Java, all the different drivers, et cetera, et cetera. Kafka, all these different ways of allowing us to connect to the data. So let me kill one thing. Sorry, not a Teams expert here. So again, this is really meant to be used. So, there'll be a new release of, if we go to, if you're a Python developer and a graph data science, we have this library. TigerGraph has their own. It's in my opinion, a little harder to use because you have to do a lot more code writing. I think some of the other vendors have it as well. But this is a library you can install. You can run it open source, so it will limit on a couple things, and it'll limit you to 4 CPUs. You won't get everything, but you can definitely experiment with your different graph algorithms. We're constantly working on moving these beta algorithms more into production quality, constantly improving the product, constantly trying to run it at scale. So we know, data is getting larger. Customers want to run larger and larger volumes. Even if you're a researcher, it's still a great product to use. It's a great tool to make sense of your connected data. And even if you just go to the documentation and see what's available, I think it's pretty interesting.
This is great. Thank you, Dave. Do you mind maybe share this online documentation in the chat?
Yeah, absolutely.
So Mark, are you saying we can have more presentations with regards to variety of ways how to import the data and how to create a graph database, those kind of presentations coming in?
Yes. So my idea, and I sent an email to the training person, Elaine at Neo4j, just to ask her if I'm on track or off base on this idea, but to have a session or a presentation that's primarily getting data into a graph database session, and there's a variety of things, and then ways of getting data out of a graph database, and there's primarily two for that. One is going to be Cypher, or this is Open Cypher now. Neo4j was kind enough to put their query language into the open source community, and then they've got a way of taking GraphQL and converting that internally into Cypher, so that you could, and Dave, correct me if I'm wrong. Once again, correct me if I'm wrong. That you could take an application that was trying to use was using GraphQL as the query language, and kind of put something between those calls and Neo4j, and you'd get the value or the speed and performance of a Cypher query. So
yeah,
that
to follow up. So we do have a GraphQL connector, interface, so you can write GraphQL. So, GraphQL is just the standard to basically build an API against any database. So there's GraphQLs for every database in our top 20 list. So it's not graph specific or Neo4j specific. You can do GraphQL to Mongo to Oracle to Postgres. So, but there is a GraphQL, so you can write the JSON type queries against Neo4j if you're trying to build a a REST endpoint. But again, just as there's different ways to get in data, there's a myriad of ways to get data out. So
yeah, and Jan Lei, you ask about tables, table formats, rows and columns. Neo4j does have the ability to output into row and column format. If you have to consume the output of the query, the graph query, in something that doesn't speak, circles and arrows.
Yes. Yeah, that's really good news.
Don't necessarily, right? Not everybody cares that, not everybody cares about the pretty pictures, right? So maybe you just want to know, give me a fraud score for this person. I got a new insurance claim. What's the likelihood that this person's fraudulent, or, this person's transaction? We see this a lot, is this a fraudulent transaction? Give me a score back. So I don't really care about the path or the connectedness. I just need a value, or, an API, end-to-end API. So, it's a database, so we can make it do whatever you need it to do.
Yeah, I do care pretty pictures, Dave.
Yeah, pictures sell, but then, when you have to put it into action.
Yeah. Cool. Anyone had any other questions for Dave?
Yeah, Dave, I'm curious about how well this scales to big data distributed systems.
Yeah, I mean, that's definitely something we're working on and we continue to work on. So I know Meredith, who's probably kind of in your space, has used it in the billions. I think they're probably at the 8 billion to identifiers. So they definitely use it for identifying those components. That's probably, right now, with hardware and how we handle things, it's probably about that scale. And we have some data scientists at larger. It depends if you don't need that real time or you're doing more data science type work.
That makes sense.
you know, we're doing some things with some distributed querying. So, you know, I think between us and Tiger Graph, you'll see different marketing and different spin on who can get bigger the faster. So, you know, definitely read between the lines, ask questions if you're thinking about. Those are probably your two biggest players as far as at scale right now, and doing it correctly. You know, I think there's some dispute on, you know, everybody publishes metrics and benchmarks, so you always take those with a grain of salt. But, you know, we've been able to get into the tens of billions of nodes and tens of billions of relationships, and we're running, like Meredith is running those weakly connected components in memory on, I think, probably a 512 gigabyte memory machine. So
yeah,
you know, we're doing some work with some of our other larger scale. So that's really why we invested. We're doing a lot of work with PyArrow. We just saw, you know, we're doing some work now where we can take data out of like BigQuery or feed it directly into the in-memory graph. And then, because, you know, we don't always necessarily need that persistent storage. So I may want to run an experiment, do some analysis, get my results, throw it away, start over. So that's work that, I don't know, I would say we're not there yet. I mean, we definitely need some work around the product to get there, but, you know, it's a harder problem for us to solve because, you know, when you get at that scale, you're using a lot of hardware resources, and then,
yep.
you know, I'm sure like you guys, you don't want to buy, you're not going to buy one or spin up a 1 terabyte memory Google Cloud machine for every data scientist. You want to think about costs and,
Yep,
this
sure.
work across my data science team. Do I really need 50 VMs for 50 data scientists? Can you fix that? So those are some of the areas that we're trying to figure out and trying to make work as we interact.
Cool. Yeah, another maybe more fundamental question, just to get a better grasp on it. You know, I feel like with the relational database, my mental picture of how data gets stored at, you know, the most granular level is something like a CSV file. I think that's really a tangible connection. For a graph database, does that look more like a JSON, or how do you actually handle data on disk?
Yeah, let me see if I can find that diagram.
Ted, they have a conference every year, the Graph Connect conference every year in the summer, and the sessions are on their YouTube channel, the Neo4j YouTube channel. Somebody last summer just kept multiplying the number of nodes by 10 and kept getting, you know, below triple digit millisecond response on their queries, and I was like, holy crap, that's
Cool.
fast.
Yeah, let me just share this.
Yeah, it seems like your power to scale really doesn't fit my intuition because it's so efficient for some of these calculations.
Yeah, so we kind of pay that price. So this hasn't changed. This will change probably in our next release, you know, later this year. But well, what they decided to do back is, you know, they did try this on, I think, Postgres, probably in like 2009, 2010, and it didn't work. So basically everything's a fixed length record. So the node is like a fixed length of 15 bytes, I think. And a relationship is like 31 bytes, and a properties some other number of bytes. So we store the node, and it has like different, you know, it has this ID, it has a couple types, and then the relationship has an ID, an internal ID we track. It has the start node ID, the end node ID, and then these keys attached to it. And then, you know, these have the relationship. So each relationship type, we know the start ID and the end ID. So we just say, if we can find the start node through either an index lookup or some way to get to the start node, then we can just find, oh, I want to know the nodes relationship. Oh, here's the first in-memory ID. Then we just follow these pointers. Here's the next. And then we just kind of hop between pointers back and forth. So we're not doing joins at runtime. We're doing joins on creation. So this number 3, joins on creation, is really kind of the bottleneck that we hit then. so we got to pay the price somewhere. And since we're ACID compliant, we pay that price on these joins. So we would actually, nodes are, if I just write nodes, I can write those really fast all day long. It's when we get into relationships where I have to lock one node, lock another node, and then we have to get kind of creative on how we create relationships. So that's why we kind of, when we talk about problems, like, the earlier talk on the volume of data, we may not always be able to ingest that volume of data. So we would think, what is a proper data store for this, and what's a proper data schema for that?
Yeah, and then in terms of like flexibility and expandability, are there, if you have to add a new type of node or a new type of relationship, I imagine some of that you can just add in incrementally here, and other varieties you might have to recalculate these relationships. Is that accurate?
Yeah, so like, and we can just add like a new, I can dynamically add these, which, we're in the NoSQL, so, you have the ability to add these, but you also have the ability to screw things up as well, just very easily. So, with great flexibility is great power. So really for us, it's then, so we can basically, like, I don't know, we can dynamically add a new label, like, I don't know, commuter. But this is in a transactional state, so, we would have to do some logic in there. Like if we had 10 million students, I don't want to do that in one big transaction because it goes into heap and it's pretty easy to crash. So we would do that in like batches of 50,000. So, we have a library that's called APOC. It's kind of everything that didn't get into the core product as workarounds. And we're kind of building some of that into the later releases of Cypher to help with that. But yeah, then, all right, how do I do this? Because now it's, a transactional state. I need to do it smartly and do it that way. So you can do it. It's just, it's not just, hey, just write a query, change 1 million. Oh shit, I ran out of memory, and that was it.
Cool, thank you.
Yeah, absolutely.
All right. Thank you, Dave, for the wonderful,
Absolutely.
wonderful presentation and the insightful demo. Very, very insightful. Thank you. We're on time for our lightning talks. Okay. So anyone want to share any little experiments you want to share with everybody today? Mark, do we have the speaker for lightning talk today? Oh.
Well, somebody posted a comment in the meetup page and said that they wanted to do a lightning talk, but if you're whoever you are, if you're here, speak up, unmute yourself, and you're welcome to do a presentation.
I see the Peter Vitos. Is Peter here?
Peter's
No?
not here.